Okay, let's get started. So this is going to be the seventh stream, or the seventh part in the implementing a transformer from scratch using Candle plus Rust. So I guess from here on out, there's not a lot of work to do because we've built the building blocks. Now we just need to compose them so that we can build out things like the encoder and the decoder. I'm just going to talk about those things. So let me get to that. So here's the transformer. We've been talking about, this portion on the left being the encoder and this portion on the right being the decoder. And these two are some extra pieces. We'll get to that. And these boxes are, what you input into the encoder and you get the output from here, right? And the same thing for the decoder. It gets an input as well. Although this is called an output embedding, this is an input to the decoder. And then it also takes the input from the encoder. That's the output of the encoder is now passed in. And then, there's something happening over there. We'll talk about it. It's called cross attention. And both of them work together to pretty much do what's called generative AI. I guess the foundations of all models today have this architecture at its foundation in some form. Of course, there's been refinements and additions to this quite a bit. But this is, I guess, the architecture that everything's pretty much based off of. So today I'm just going to talk about the encoder, this part. You might be wondering, we've already sort of talked about it and built it. We've built this block. We've built the input embedding. We've built the multi-head attention. We've built the feed-forward block, and we've also built the normalization layer. And to top it all off, we also built what's called the residual layer, which we saw in the last section, which was basically, you see this, that the multi-head attention block as well as the feed-forward block, both of them are sort of sandwiched between, an add and normalization layer. You could actually implement that as your residual layer because, one portion of the input before it goes to the multi-head attention goes to that, and the output of the multi-head attention is again passed in. So that's what you normally refer to as a residual layer. So we've talked about that, and we've also talked about why you need that, because you have this problem of vanishing and exploding gradients, which we went into in the last one. So you can probably look at that if you're wondering why that is. But let's get to, again, our focus is the implementation and nothing else. Using Candle, how can we basically write that transform architecture in Rust? So over these last few streams, I've been observing that Candle is pretty close to PyTorch. They've kept that theme going, or they've kept that goal. I would say they've upheld that goal quite a bit. But there are some pieces, you obviously Python's not Rust and Rust's not Python. There are some situations where you might have to think a little differently and look at things a little differently. But for the large part, you would see that it's pretty similar. Okay, so to get to it, if you look at the encoder block, the first thing that you notice is this is the encoder block, all right? We have a multi-head attention in it. We have a feed-forward block, which we already defined. And then we've got these two sandwiched layers. Both of them, the multi-head attention and the feed-forward block, is sandwiched between two residual connections. So I just put that in a vector, and I call that my residual connections. So I'm able to create an instance of the encoder block and also then, push it forward. That's how I would put it. That is basically call the forward method of the encoder block on it so that it makes progress. That means it moves. So this whole thing, the input embedding and all of that will move when you get the output of it. And that's exactly what's happening in the forward method. The first residual connection is applied to the multi-head block, which you would see here, MHA. And the second one is applied to the feed-forward block. That's it. That's about it. That's how you'd implement the encoder block. But that's not interesting. The interesting thing is you'll see this NX over here. This is actually repeated a couple of times. I don't know, it's 10 times or whatever. I'm still looking at that and trying to understand if there's a correlation between the number of times you need to, repeat that block. I've just gone ahead and done a test. I'll show you that. But you repeat that n times, and then whatever, so the previous iteration's output is going to be the input for the next iteration. Likewise, it goes on to the number of iterations, and then the final output is what is fed into the multi-head attention block in the decoder. We'll get to the decoder part in the next stream, just to keep this stream smaller. But if you notice, that's exactly what's happening. So let me sort of show you what's going on in the source code. So there's a bunch of other, because I said the model is pretty much ready. So that's good. But if you look at the encoder module, you'll see that this is the encoder block we've been talking about. And you'll also see that this is the encoder. So the encoder is nothing but a sequence of encoder blocks. That's how I've modeled it. It's an encoder, it's a vector of encoding blocks. You also add a normalization layer to it because you just put this inside of it. So fine. Towards the end of it, but that's fine. That's actually part of the paper. So at the end of it, this is what the encoder is. So what you do is you create an instance, again, a new, and then if you want to forward it, you basically take each encoder block, you iterate over them, and then you call their respective each encoder block's forward method. And that way you pass in the previous input into the next input and you keep going forward. And finally, you normalize it, and that's your output of the encoder block. Now, if you want to look at the output, I've actually written a start to end sort of an example because that's how I like to think. So everything that we've done in the past, we've sort of made use of it over here. We've got the tokenizer, we've tokenized our, whatever English text that we have. So we've got those tokens. You can see the tokens over here. We've got the IDs of those tokens as well. We do all of that. We get our vector embeddings. We get our position embeddings. And then we basically put together our encoder input. That is this input. So this plus this gives you the encoder input that goes into the multi-head attention block. So we get that. And then we start creating our encoder blocks. That means we start creating, in this I've just said, let's start with 10. I'm not sure if 10 is the right thing, but just said 10. And then I create 10 encoder blocks, each with a multi-head attention and a feed forward block. And that becomes my encoder, which is, where's that? This part. Lastly, once that's done, I'm going to go ahead and instantiate my encoder, of course, and then call the forward method on it. Again, if you see this, the whole architecture composes well. It's like, that's why, I in the beginning, I talked about, it's basically tensors that are flowing into these blocks. The blocks are transforming them in some way or not transforming them if it's a pass through. And then you're passing it on to the next block. And then you repeat that multiple iterations. So this architecture is pretty modular and it's pretty composable. And that's exactly what you can also do in Rust, because Rust has this composition based. It's very good when we're talking about composition based programming versus this object oriented style. So this works really well with Rust as well. Additionally, I also think that, when it comes to parallelizing stuff, this architecture actually lends itself well. I haven't looked into, how well this is parallelized. I'm pretty sure this is parallelizable pretty well. But the degree to which I'll have to look into it. But yeah, that I can also sense that. The next thing is you call the encoder, and then you get the encoder output. I put that example together so we could pretty much just run it. So let's just say, so this is a test. So I can just show you that I am running the right test. So this is the test encoder. So if I just do that, we will now be able to, as you can see, we've tokenized stuff. We get the IDs for each token. As I said previously in the previous streams, each token is just a word level token. We're not doing sub word level tokenization, etc., because we want to keep these simple. The idea is we go through each of these the entire architecture piece by piece. We get to a point where, we start analyzing why this stuff actually works. We want to get to that part, which will come later and in some time. But right now, I think the model is almost ready. We've also got the decoder stuff that's ready. We put both of them together and create the transformer. That's the final thing. But anyway, so you should be able to see the stuff over here. You see that if you see this is going to repeat itself 10 times, I'm not going to scroll through the whole thing because it won't make sense. It's just floating point numbers. But yeah, so this is going to be like you're going to keep repeating this 10 times over. So again, it repeats final attention scores and then softmax, blah, blah, blah. Then, yeah, and then you will again get to final attention score. So you basically repeat this 10 times. If I scroll to the top, you get, yeah, these are pretty heavy matrices. So, uh, yeah. So you see that we got the vector embeddings. I forget this is just temporary stuff that I wanted to print and figure out. Then you've got the position embeddings. This is my encoder input. Once it goes in, you go through those 10 runs and then you get the output. The output is towards the end. So yeah, here's your output. Here's what you get. Now this is one iteration in the encoder. So I presume even now we can do things like classification with the encoder. So what's happening over here, I'll also sort of briefly talk about that because we touched upon it. This part is the encoder, right? So all of this is the encoder. Whatever comes out of the encoder is being passed into the decoder. So previously the multi-head attention was, the input itself, you were trying to find, affinity scores or retention scores with the input, whatever input was provided. That's the Q, the query times the key transpose divided by, uh, the square root of bk, etc. All that formula we've seen. But here, the key and the value in this multi-head attention comes from the encoder. And you're trying to measure, or rather talk about, some sort of attention scoring between the encoder's input versus the decoder's input. So you pretty much use this for something like, let's say, translation. So if this was a target source language, this is a target language. You could, you know, sort of do, you could sort of pay attention to, what is being said in English and contrast that with what does that look like in, let's say, Spanish, or forget Spanish, any Indian language like Telugu, Hindi, Tamil, etc. So you'll try and do that correlation, and that's sort of happening here at the cross attention phase. And then that's what comes out. All right. So that's good. Now, a couple of other things that I also wanted to talk about was Candle from the framework. There are certain areas where, they're not really making use of the, what you call the, for example, dropout is a type that's available to you. It's a convenience type that you can do. We've talked about dropouts in the previous stream, so you can look at that. Basically, this is what we need. It calls this dropout method, which enables you to drop out portions of your tensor for various reasons. Either it's an attention drop or an embedding dropout or whatever it is. But anyway, it's an implementation that's available. But one thing I've noticed is they don't implement copy and clone. And I'm not too sure why. It would be nice to actually do that. It would make things simpler, right? So that's not happening here. I guess they probably omitted that or missed it. I'm going to anyway check on their Discord thread. But that's another thing that I've noticed. That would really help because, this is a cheap copy because this is just an F32. It should certainly implement it unless there's a real reason not to. So that's one. The second thing is I had to change the implementation a bit because, these copy stuff was not really working out and I wanted to actually write idiomatic code, Rust code. So for example, if you take a look at the decoder block now, not the decoder, the encoder and the encoder block. If you take a look at this, I had to actually go ahead and, where is that? Yeah, I had to actually build something called sublayers in my residual connection because initially my residual connections layer was built using traits, but now that's not really something that works because There's a lot of copying that I need to do, but that's being prevented. So what I've done is I basically used an enum. That's another way to do things. Wherein here, I was basically looking at the sublayer saying anything that implements sublayer input, which is measured here. So if anything is a residual layer input, go ahead and put that in a trait, and then it'll implement that method. That should be done. But I kept running into type issues and a lot of things that just didn't make sense when you wanted to write idiomatic Rust code. So I switched the design and actually put it into an enum. That's easier. So that's something that you can still do. But yeah, it would have been easier if uh, you had things like the right types actually implementing those Marco traits like copy, etc. That would be actually ideal. Let's find out. I'll check with them, and I'll let you know in the next week why. Okay, so that's kind of where we are. So we're getting some output. None of this makes sense right now. This is just garbage. We'll actually get to the training phase. We'll have to tweak the model to see, if we're doing the right things or something's missing. We'll only know by then, but at least the initial tests run. Okay, so that's about what I have for this stream, I guess. And I'm pretty sure I didn't overshoot this time. I'm actually happy. So yeah, that's it. Have a good weekend.